So welcome to the second Distinguished ECS lecture of this year. This time it's hosted by Materials Science. I bring apologies from Dean Adams, who is unable to be here today. But rather than me introduce our distinguished lecturer, I would like to introduce Dr. Bob Wallace, who is one of Dr. McIntyre's collaborators and former colleagues at, very appropriately, Texas Instruments, who very kindly gave us this very nice auditorium. So, Bob?
Thank you, Amy. I'm wondering if I should use this.
Can you hear me better? All right, let's try this. So it's a pleasure to welcome Paul McIntyre back to the UT Dallas campus. He's been here before a few times, and he was here early. We were talking about maybe 12 years ago when we were kind of building things at that time. So he's quite familiar with the campus and the evolution. The one thing about Paul is that he is really very timid about his CV, very difficult to find anywhere online. So I had to dig deep in my archives to do him justice from his brief bio that we see. Let me point out, first of all, that he received his bachelor's degree, Bachelor of Arts and Science, I guess, BA Applied Science, in Metals and Materials Engineering at University of British Columbia back in 1988, and then wandered off to MIT to get his doctorate in ceramics in 1993. He did a postdoc there for a year, and then he moved over to Los Alamos National Lab, working with Nastasi, as I recall, in the materials division there. And after that was when we met, essentially, when he joined us at TI. He was hired by Don Shaw, who's down here in the front as a part of the Materials Science Laboratory, part of the Central Research Labs then at Texas Instruments. So Paul is really well known in really what I'd say oxides in general, and that early work he did involved high TC cuprates and worked in the areas of ferroelectrics eventually, barium strontium titanate systems and so forth. That's why he came to TI to work in that area at the time. And I believe it was something around, was it 1995 or so, when you moved to Stanford at that point? 97. He moved to Stanford. And he started as an assistant professor at that point at Stanford in the material science department there. Well, after that, he became very well known amongst the faculty there, I can assure you. He was very successful in the work he's done, and what he's been known for maybe in the last decade in particular has been his work on high-K dielectrics and atomic layer deposition. And more recently, he's transitioned more into the energy world, as we'll hear. But essentially, he has now the Rick and Melinda Reed Professor in the School of Engineering. He is a professor of material science and a professor of photon science as well. He is a senior fellow at the Precourt Institute for Energy at Stanford. And he was chair of the Department of Material Science and Engineering from 2014 to 2019. So he really led that department very well. As you may know, they're one of the top-ranked departments in the country. After he did his turn in the barrel there, and he's decided to become a director at Stanford Synchrotron Radiation Light Source. So he's now immersed in the world of DOE and the funding and a very prestigious laboratory that's, I think, going to be in the midst of some upgrades and so forth as a part of that. So very exciting time. From his publication point of view, Paul's published over 300 papers, actually, and he has citations, if you count Google Scholar, for example, over 15,000 citations. So it's very well cited in his work overall. He also has some patent activity. I think he has up to 9 patents right now. and it's certainly part of his portfolio. He has several awards over the years, like 2 IBM faculty awards, not just one. He's also been an SRC Inventor Recognition Award, and in the Materials Research Society, he won the Woody White Award in 2011. So please join me in welcoming Paul to UT Dallas. We'll enjoy hearing your talk.
All right, thank you. Thanks, Bob, for that great introduction. And I'm delighted to be here today. It's wonderful to see so many familiar faces, and it's been many years in some cases since we've met, so it's terrific, and I feel honored to have Don and Luigi and others here who've been important in various parts of my career. As Bob said, I've had the opportunity to visit UT Dallas a number of times, and came here, I think, for the first time in 2007. And I have to say, it's a remarkable transformation that's happened, the growth of the campus, the strength of the faculty and the students, and the sort of the institutional resources behind the university's growth are all very impressive. And I think there's great future potential for UT Dallas as well. So it's particularly exciting for me to be here as a distinguished lecturer. Today I'm going to talk about new things in my group's research. As Bob said, when I came to Stanford, not long after that, I started up an activity in atomic layer deposition and really looking at the interfaces between deposited oxide materials and various semiconductors, trying to understand how to characterize those things with sort of spectroscopy, electron microscopy, and also with device relevant measurements. That really dovetailed in various different directions. ALD has been a tool that we've used increasingly for energy applications, for making new kinds of catalysts, for surface functionalization of materials for various applications. And it also led to an interest in more complex sort of nanostructured semiconductors, because ALD is very amenable to coating those structures uniformly. So we developed some competence in growing single crystal nanowires and other kinds of semiconductor nanostructures to go along with the ALD. So today I'm going to talk about some of the recent work that kind of builds on that story. But I want to start by, I have metastability in the title of this talk, Metastable Materials for Optoelectronics. I want to go back to my background as a metallurgist and talk about metastability in the way that I first encountered it in school, and that was in looking at the iron-carbon phase diagram. So when I was an undergraduate, this kind of thing was sort of our bread and butter. The iron-carbon, kind of weak. All right, well, we'll make do. So the iron-carbon phase diagram, this is obviously a map of stable phases that exist. This is just the corner, the iron-rich corner of a much larger phase diagram. It's an interesting phase diagram from a thermodynamic perspective. There's a lot of phases on it. There's a eutectic reaction that occurs around here involving a liquid and 2 solids solidifying it from it. There's also this eutectoid reaction involving a solid solution, similarly phase separating into 2 different compositions below a particular temperature. And this is the region in which a lot of the metallurgy done to develop steel was performed over a period of centuries, many centuries, to develop the technology to make metals for many applications. Initially, a lot of interest, obviously, in military applications and making things like these sharp edges for weaponry. In addition to the information that's sort of encoded on the phase diagram that tells us about thermodynamic equilibrium, there's metastable phases that are important. And The formation of these metastable phases at temperatures in this range in here is, oh, thank you, Bob. Much, yeah, I'll be judicious here. This range of composition is the one in which people have also studied metastability and the ability to form phases that are not on the equilibrium phase diagram by rapidly quenching through this composition range to lower temperatures. This is the range of composition and temperature in which we can make a material called martensite, which is the M here in this temperature, this isothermal transformation diagram. And I'm not going to get into the details of this, but this really maps out the kinetics of formation of these metastable phases during rapid cooling. So if you understand the kinetics of the formation of these metastable phases, you can make materials that have a very hard kind of steel that is appropriate for tool making and for weapon making. If we look microscopically at what happens in the process of this kind of metastable transition through cooling, we make a phase of iron that is alloyed with carbon that has a body-centered tetragonal structure. This is a highly strained crystal structure forming within the FCC austenitic phase of iron. And because of the very high local strains, it introduces a lot of dislocations and other defects. And the presence of dislocations and crystalline defects, which we can see even evidence of in these optical microscopes, the presence of all of these different crystallographic boundaries makes it hard for additional dislocations that might form during deformation to propagate. So this is what makes it such a hard material. It's possible to engineer the amount of hardness increase depending on the rate of quenching and the composition. And people have played these games for many decades as a large industry, many industries based on this. But it's an example of how metastability can be utilized to really revolutionize the development of technology and really to change human history. I mean, if we didn't have martensite, history would have been very different. So there are many other examples of metastability. This is one that comes sort of from my own undergraduate background. But today I'm going to talk about metastability in different contexts. Four of the research areas that are currently active in my group involve metastability in one form or another. I'm going to talk about two of these four examples here just because of the time constraints. One interesting case of metastability that's attracting a lot of interest right now, Bob mentioned ferroelectric materials as being something I've been interested in. Well, there was a discovery about 8 years ago that hafnium oxide, when it's synthesized in an appropriate way, something like that rapid quenching used to form martensite, but in this case it's usually accomplished by some doping or the addition of stress. It can exhibit an orthorhombic phase. It's a metastable phase of hafnium dioxide, something that isn't on the phase diagram, but it's a ferroelectric material, so it can exhibit a permanent polarization that can be reoriented by applying electric field. This is a form of non-volatile memory. So the thing that's exciting about that is the semiconductor industry already knows how to make transistors with hafnium dioxide as the gate dielectric. So with that industrial background, it's possible to make high-density ferroelectric memories in the form of a transistor-like device. And what we've been working on recently is making such devices and understanding how this orthorhombic phase can be controlled, how its formation is controlled. And if one does this correctly, it's possible to make transistors that can be programmed in an analog fashion, where we can actually go through multiple states, multiple threshold voltages for the device, depending on how much we've programmed the polarization of the material. In this case, we can access 32 individual states of memory. So this is interesting because in some ways it mimics the linear potentiation of a synapse in the brain. So there's an interest in these kinds of devices for neuromorphic computing. I'm not going to talk about this today. Another area where metastability is important is actually in heterogeneous catalysis. If we perform a chemical reaction on the surface of a metal, it's very often the case that the metal surface will be transformed into some metastable structure. And it's that metastable structure that actually controls the catalytic performance of the material. This is an example of some XAS data that we took for iridium, which is the best water oxidation catalyst out there. And it's well known that iridium forms iridium oxide surface coatings, but we actually see the formation of metastable forms of iridium oxide that wouldn't normally be formed in a typical thermal process as a result of the interaction of the water with the iridium oxide surface during water oxidation. If we take away the applied potential that's being used to oxidize the water, this metastable form of iridium oxide disappears. So in this case, it's metastability, but metastability that has a pretty transient lifetime associated with it. What I'm going to talk about today are the other two examples. And the first one I'll talk about is this one here. This is showing the photoluminescence spectrum for an inorganic halide perovskite thin film, cesium, lead, bromide, iodide. This is an alloy of cesium, lead, bromide, and cesium, lead, iodide. And what happens in these materials is something that I think is really fascinating and hasn't received enough attention yet. A lot of people are looking at these perovskites as photovoltaic absorbers. Some people are looking at them as light-emitting materials. But when we make these alloys with different anion species, we find light can induce, and even electron and hole injection into an LED can induce a phase separation. So the initially homogeneous, thermodynamically stable composition spontaneously phase separates into regions of high iodide concentration or low iodide concentration. And what that does in practice is it produces a redshift in the photoluminescence. The electrons and holes become trapped in the regions of smaller band gap, and therefore they emit at a longer wavelength. This can happen, this process of phase separation can happen over a period of minutes at room temperature in these materials, and it can be completely recovered after resting the material without any carrier injection after a period of a couple of hours. I think there's a real opportunity here to make optoelectronic memory based on this kind of phenomenon, which really hasn't been realized yet. And another example I'll talk about today is metastability in a different context. These are semiconductor nanowires where we've formed a metastable alloy of germanium and tin. So tin has a limited solubility in germanium, but if we can exceed that solubility through crystal growth tricks, it's possible to make much more tin-rich alloys that have really interesting optoelectronic properties. So I'll talk about that. So those are the two topics I'll focus on today. The first one, inorganic halide perovskite light emitters. So there's a lot of excitement about these halides, and that's because really they're remarkably good optoelectronic materials. They can exhibit emission wavelengths or absorption over a wide range of energies just by tuning the composition. So there's a whole class of what are called hybrid perovskites that involve complex organic ions in the perovskite structure along with inorganic ions. I'm focusing here on the purely inorganic halides. There's a lot of those as well. So, but in any case, we can tune their properties both by changing composition, and there's a wide array of different ion species we can put on this perovskite lattice. And also, as is typically the case with these kinds of materials, we can tune their optoelectronic properties by using size effects. So by going to very small dimensions, we can also control their absorption and emission characteristics. The phenomenon I'm talking about here is a little different. This is a situation where purely by injecting electrons and holes into this material, either by shining band gap light on it or by injecting it through electrodes, we see the ability to program the emission characteristics. And this is shown here in some nice work from this published reference a couple of years ago. One of the first groups to report on this was the group of Mike McGehee. So Hoke was a student in his group. At the time, Mike was a colleague of mine at Stanford, and I remember him, coming to my office and showing me these results on this shift in luminescence wavelength. And the only thing I could think of at the time was that it must be some kind of a compositional adjustment in the material happening spontaneously as a result of the light shining. They were able to show that it wasn't induced by any kind of a heating effect from the light. It was really just the absorption of the light, of the bandgap light, that was doing this. And they also could show evidence in X-ray diffraction that they would see some shift in peak intensities, suggesting the formation of more iodide-rich and bromide-rich regions. So it all sort of made sense. But the thing that's remarkable about this is it's happening at room temperature. And if you think about what we do in making optoelectronic devices, we generally try to make nanostructures with some kind of a length scale, some kind of a composition difference between the material inside the quantum well and the material on the outside of the quantum well. We engineer those structures by epitaxy and by other kinds of means to create that structure. And then we use that to determine the emission wavelength or the absorption characteristics of the device. This is the inverse. This is shining light and having the material spontaneously reorganize itself in order to have a different set of properties. So I think this is a really exciting phenomenon, and one that we should look at seriously and try to understand, and also see if there are other examples of light-driven phase separation that could be important. So this is the kind of picture that was painted at that time. I think it's all the data that people have reported so far are consistent with it, but there's still a lot we don't understand about this process. And it happens not just by shining bandgap light at one of these materials. If we make an LED, as this group reported a couple of years ago, we see the same kind of effect. So we can tune the emission characteristics of the LED by just changing the composition of the various layers in here. But when we apply a bias and inject electrons and holes into it, we see this shift, this red shift in emission wavelength. And if we stop applying the bias and just wait, it goes back. It returns to its original structure, to the thermodynamically stable structure. So as I said, I think this is this particular kind of effect where we can use electrical biasing to move the iodide and bromide ions and have them effectively demix. I think this could be the basis for some interesting technologies. So we started growing these materials in my lab by a technique called chemical vapor transport. Some of you will be familiar with this who work on TMDs and other two-dimensional materials as a common technique. It's related to chemical vapor deposition. Basically, we use powders that are heated in crucibles. They evaporate, and by controlling the composition of the powders, we can control the composition of the film that we grow. In this case, we're growing on a strontium titanate single crystal, 100 oriented single crystal. That's also a perovskite. It has a very large lattice mismatch to this particular composition, but we're able to get a reasonably good crystallographic texture of the resulting film. These films in this picture are about a micron thick, but you can see they're very large. We have very large area coverage and large crystallite sizes. There's some misorientation of the crystallites. They've grown together. We can see some interesting kind of boundary structures, but they're on the order of about 100 microns on a side, and in some cases we can grow crystallites significantly larger, millimeters on a side. So these materials are nice for studying these kinds of phenomena because, unlike the typical solution-derived perovskites, the grain sizes are much, much larger, and therefore we can separate out any effects due to the illumination or the carrier injection in the bulk of the material from effects related to grain boundaries and other sorts of defects. What we see is in the PL spectrum, this is the initial state. This is after soaking in bandgap light for maybe 30 minutes. We see the formation of this this double peak, so the red-shifted peak, and we can actually watch the dynamics of this in the PL experiment. So we see the same kind of phenomenon that other groups have reported. And in this case, we believe the composition of the perovskite is something like 5% iodide and 95% bromide. We can characterize that with techniques like energy dispersive X-ray spectrometry mapping, and we see indeed we've got the right elements very uniformly present in these layers, and the strontium and titanium in the regions where the film is not present. So we have well-controlled and uniform composition with this CVT process. And we've been trying to understand one of the key features of this, which is, what is the length scale of the phase separation? It's pretty clear from the diffraction evidence, and I'll show you some in a couple of slides, that there is a real phase separation happening. We can see that in the formation of shifted X-ray diffraction peaks. But to date, we've been unable to really determine the length scale, and no other group has been able to do so either. When we look at optical microscope images, this is for images where we're detecting emission at different wavelengths after varying amounts of soaking in light. Once again, we see this red shifting occurring, but we don't see any kind of a change in structural features that we can attribute to the phase separation, at least at the length scales we can see in optical microscopy. What we have done, though, with these measurements is been able to determine in situ the optical constants of this material as the phase separation is taking place. So these materials exhibit a well-defined exciton peak in both the refractive index and the absorption coefficient. And during the phase separation process, that exciton peak splits into two, consistent with two different compositions coexisting in the film at the same time. And the fact that this happens means that we could imagine making waveguides and other sorts of structures and manipulating their optical properties and the way that light would propagate along them as a result of carrier injection. We look at X-ray diffraction and just do a typical, Bragg scattering experiment. One of the things that's characteristic of this kind of phase change is a tremendous increase in the amount of diffuse scattering around the Bragg peaks after soaking the material in band gap light. If we wait an hour or two after shutting the light off, it recovers to the original diffraction peak. So we don't do any kind of permanent change to the material. It's recoverable on an order of minutes to hours. And once again, this is not a thermal effect. So if we simply heated the sample to a higher temperature, as the light might do, all we do is we shift the peaks as a result of the thermal expansion coefficient effect. In fact, these materials have a pretty large thermal expansion coefficient. We can see a pretty sizable shift here in the peak, but no increase in diffuse scattering. So that's a different thing. So just to summarize sort of where we are with this right now, we are studying the dynamics of the phase separation, trying to determine the rate constants, and in particular doing this at different temperatures to see if the rate constant for phase separation can be related to known activation energies for ion diffusion in these materials. And we've also been doing a more careful X-ray diffraction characterization. This is a reciprocal space map, and this shows the formation of a second peak after the illumination of these samples, consistent with a more iodide-rich composition. So we believe that these regions, these small regions, we believe they're certainly microscopic or nanoscopic in size, are responsible for the bulk of the emission, this red-shifted emission, after the phase separation has taken place. We're still looking to understand morphologically what the length scales are, how these things are distributed through the material. And one of the techniques we've been using, now that we can grow the films thinner, is cryo-electron microscopy. These materials are very beam sensitive, so we need to do the imaging at cryogenic temperatures. So we're looking for evidence of the phase separation now in cryo-TEM. That's just starting. So just to summarize, as I said, this is new stuff, so it's not a complete story yet. we find that initially stable halide perovskite alloys become metastable as a result of electronic carrier photogeneration or injection. It's consistent with a self-reinforcing phase separation driven by a reduction in carrier potential energy. Basically, as the phase separation happens, the carriers can trap selectively in more iodide-rich regions, and therefore the emission wavelength shifts. The detailed mechanism, whether this is like a nucleation growth process or spinodal decomposition, is not understood. We'd like to investigate that and understand it. But if its rate and length scale could be controlled, this electronically driven phase change could be used in novel programmable optoelectronic devices, we think. So that's from an application standpoint what's driving us. So in the second part of the presentation, I'll talk about our work on these germanium core, germanium tin core shell structures, core shell nanowire structures. And these are just a number of images showing what these look like. These are single crystal wires that we form. We find when we section them, they have a complex structure. This is the germanium-rich core. They have this nice hexagonal faceted cross-section. This is the tin-containing shell, and we see these interesting spoke structures I'll say something about. And at high resolution, we can see that these are truly single crystals and we don't see any evidence of dislocations in them. So why are we interested in structures like that? As we add tin to germanium beyond the solubility limit, we can start to modify the band structure of the material. So for silicon, we have an indirect bandgap material, relatively large bandgap, and it's indirect, meaning that in order for this transition to take place, we have phonons or other species and other processes involved. It doesn't make for an efficient light emitter. We're interested in systems like germanium tin because they are, in principle, compatible with silicon photonic devices and circuits. They're group 4 compatible, and they can be synthesized at quite low temperatures. And by sufficient addition of tin to the germanium, it's possible to make them laze. So we can make lasers and LEDs out of germanium tin. The first germanium tin laser, this is an edge-emitting laser, was demonstrated by researchers at the Forschungszentrum in Jülich, Germany, in 2015. And they observed lasing up to about 110 Kelvin in these experiments. They attributed the inability to sustain it at higher temperatures to the presence of defects that were acting as non-radiative recombination centers. Now these things are grown generally on a relaxed germanium buffer layer on silicon. There's a lot of misfit in this system, a lot of opportunities to form dislocations, and also the possibility that at these low growth temperatures, there may be other kinds of defects forming. So those would be the candidates as recombination centers that we have to pay attention to. The advantages of this system, we can tune the properties of the semiconductor by tuning the tin composition. It's predicted that somewhere around 10 atomic percent of tin is the crossover point from an indirect gap material here to a direct gap material. And as I said, there's the potential for this to be silicon CMOS compatible in a way that many 3-5 semiconductors are not. The challenge is, though, we have low equilibrium solubility of tin and germanium. We need to get to at least 10% in an unstrained material to achieve the direct gap. But the solubility limit, according to the phase diagram, once again, is about 1 atomic percent. So that's a problem. In addition, there's a large misfit. The diamond cubic form of tin has about a 13% larger lattice spacing than germanium does. So even at 10%, we're talking about a 1.3% or so misfit. And that's sufficient for generating dislocations during growth in most cases of 2D epitaxy. Another problem that we have is even if we avoid the dislocations and we make a highly strained germanium tin, that compressive strain is actually itself able to modify the band structure of the material, and it makes the direct transition less likely. It basically acts against having a direct transition. In fact, what we'd like to have is a combination of some tin and some tensile strain. And so by adding tin and growing the film on any of the substrates we would normally choose, we're going the other way. We're putting it into a state of biaxial compression, and that's not good. So there's a lot of challenges here. If we could do these things, though, and we could make nanostructures with germanium tin, there's a lot of interesting things that could be done. We've been interested in the idea of using nanowires because nanowires can, in principle, if you form them as a core and grow a tin-containing shell around them, they can act as a compliant substrate for epitaxy. You can elastically store the strain in the germanium core and have a relatively strain-free shell once you get beyond a certain shell thickness. And that means it's possible to, at least in principle, make defect-free materials that, or dislocation-free materials that are unstrained with tin in them. If that can be done, it's possible to make sort of photonic crystal systems where we can direct light onto particular nanowires and perhaps achieve high gain media in that way. We can also play games with plasmonic devices. So having a nanowire sitting on its side on top of a passivated silver film. Silver is an excellent material for supporting plasmon resonances, and that can couple into the wire, and that can be another way of delivering energy to the wire and to ultimately causing it to emit. And making structures like resonators, taking advantage of whispering gallery mode resonance by taking advantage of perpendicular nanowire arrays on silicon or other substrates is another direction that we're interested in. So nanowires could be useful if, in fact, we can grow these kinds of structures and achieve the large tin concentrations we need to get to a direct gap. So the way that we do this, for many years my group has been working on epitaxial growth of germanium and silicon nanowires on various substrates. It's possible to do with the vapor liquid solid process. Start with a catalyst. In our case, we use gold. Put these gold nanoparticles or patterned nano clusters of gold on the surface. Pass germane gas over it. The germane decomposes on the silver. It absorbs enough germanium to form a liquid droplet. And this liquid droplet has a high surface tension, so it tends to form a nice hemispherical cap on the surface. And as more and more germanium is added through the catalyst, we grow a single crystal nanowire. And these can be grown as vertical forests, vertical arrays of wires at quite high density. We can control the density by controlling the density of the catalyst. And we can grow them pretty much as long as we want them. And then at some point, introduce a tin precursor into the CVD process. In our case, we use tin chloride. And what you might think would happen is we just continue the axial growth of the wire, and it would go from being a germanium wire to a germanium tin wire. But there's a lot of interesting surface chemistry involved here. So it turns out, in fact, that doesn't happen. As soon as we introduce tin chloride into the CVD environment, the axial growth virtually stops, and it transitions to shell growth. And that is likely because when we grow a nanowire with germane in a hydrogen CVD environment, the surface of the germanium wire is at least in a dynamical sense, hydrogen passivated. As soon as we introduce tin into this process, tin is a surface segregating species, and it forms a very weak bond to hydrogen. And we believe that the tin actually disrupts the hydrogen termination very effectively, and suddenly these sites that were passivated by hydrogen are now available for crystal growth, and we see radial crystal growth. So it's a very clear phenomenon. I'll show you the pictures here. So these are the germanium nanowires where we didn't add any tin chloride to the process. And this is if we grew the same nanowires and then did 30 minutes of tin chloride containing growth. Germane's still present, obviously, because we're making an alloy shell. You can see that really there's no axial growth at all, and in fact there's just this radial growth. And they grow with this really interesting kind of fountain pen appearance, or maybe rollerball pen, I guess. That's the gold-containing catalyst, but it's gotten a lot bigger. So there's still a lot of residual tin in that catalyst after the process is over. It solidifies at the end of the process. And you can see that there's some interesting tapering and and change in the facet structure around the tip. So we believe that the tip influences the crystal growth, the radial crystal growth as well, and it causes this. It's a bit like the old Coca-Cola bottles kind of shape. We studied the crystal structure of these wires quite carefully. These are data obtained at a synchrotron source, and I'm sad to say not at SSRL. We don't have the capability to quite do this kind of measurement at SSRL. This is a nanobeam synchrotron beamline at the European Synchrotron Research Facility. What this shows is germanium, diffraction from germanium-111 planes. So these are the planes that are perpendicular to the wire axis. We can see the germanium-111 peak from the substrate. It's very, very sharp, very small because it's a bulk substrate, single crystal, high quality. But we find that shifted because the germanium tin is growing coherently around the germanium, and all of those lattice spacings are really dictated by the germanium tin shell. We have a shifted lattice spacing, but they're in line in reciprocal space, showing that we've maintained coherency at the interface. We can also see that there's a much greater spread here in the perpendicular direction, and this is because we're diffracting from finite-sized nanocrystals, not from a bulk substrate. But this is consistent then with coherent epitaxy of the shell around the core with about 0.6% tensile strain in the germanium core, and therefore that's consistent with around 4 atomic percent tin for this particular growth. And once again, we can look in with high-resolution TEM. We can see this is single crystal-like material. We can see the Fourier transform of it. The interesting thing is if we look in the same growth at the germanium tin film that forms on the substrate, on the germanium-111 substrate, this is what we form. It's incredibly defective. It's full of dislocations and stacking faults. So this shows us that the presence of a compliant germanium core substrate induces a local epitaxy that's very high quality. But if we grow on a bulk substrate where we have this large lattice mismatch, we form a very defective film under these growth conditions. What does that do for us in terms of properties? So if we look at the room temperature photoluminescence from these structures, we can decompose the photoluminescence peak into the various emissions from the L and gamma valleys of germanium and germanium tin. We see that this germanium tin, that the germanium tin gamma valley peak makes a strong contribution to the overall peak, but this is only 4% tin, so we haven't gotten all the way to a direct gap material yet. But we can see even adding just this small shell around the germanium, the shell thickness here is about 80 nanometers around a 40 nanometer diameter core with 4% tin. We boost the photoluminescence. We shift it, of course, because the change in composition and strain, but we boost the photoluminescence intensity by a factor of about 30 or 40 just by coating the germanium wires with the shell. So this obviously has a lot of beneficial attributes. In order to be able to boost the tin concentration higher, to get to 10% or higher, we needed to do a pretty careful study of the CVD process in our reactor. And what we found when we look at things like the shell thickness, diameter as a function of shell growth time, or more interestingly, actually, the cross-section area, effectively the cross-section of that wire as a function of growth time, we find some interesting things. First of all, at longer times, we see this linear relationship between the cross-sectional area deposited and the growth time. And this is consistent with mass transport limited growth of the shell in these longer times. At shorter times, there's a much lower rate of growth, and in this case, we believe that this is limited by the strain that exists in the shell at these small shell thicknesses. When the shell is really thin, there is the compliance of the core substrate is not great enough to avoid storing some strain in the shell. So the germanium tin that's being deposited here is at a higher energy. There's less driving force for it to deposit because it's under strain. As the shell becomes thicker and thicker, more and more of the strain is transferred to the core, and the material that's then deposited is at effectively a lower chemical potential, and therefore the rate of deposition increases. And this linear scaling, as I said, is consistent with mass transport limited growth. So we needed to look at things that we could engineer to control the mass transported limited growth. One of the things that we found is that tin chloride mass transport played an important role in this process. Another thing that was very important was the density of the wires. So what we found is that when we had the initial germanium wire forest was very dense, the wires actually tended to grow with a bent morphology. And often they were bending toward regions where there weren't a lot of wires, as if we were supplying more tin to that portion of the shell, and therefore they were under a greater strain, and that was causing this bending effect. If, on the other hand, we had too few wires, we could be supplying too much tin for these growth conditions, and actually the tin chloride would start, we were providing so much we couldn't incorporate it in the crystal, and we would start to precipitate tin on the surface of the wires. So it was necessary to find sort of a happy medium to be able to grow straight wires that didn't have defects in them. So there's a lot of work that was involved. My student Andrew Meng did a really nice job on this. And just wanted to show this as sort of a picture that we have in mind of what's going on here. We're incorporating tin far above the solubility limit. We're doing this with a gas phase CVD process. And so what we believe is happening is that tin, which is this surface active species, is forming something like a wetting monolayer on the surface during the CVD. And the amount of tin that gets incorporated is dictated by the sort of dynamic balance between the rate at which steps are advancing on the surface and the rate at which we're replenishing the tin on the surface and maintaining this tin monolayer. And if the step advancement rate and the tin arrival rate are controlled, it's possible to force in a metastably high tin concentration during the growth. By controlling the growth process, Andrew was able to achieve pretty high tin concentrations. This is I'll show this first. This is a annular dark field stem image. These are FIB sectioned wires, so we've cut longitudinal sections through these wires in the FIB. And then this is the line scan, the line that Andrew scanned down in the EDS analysis. We find that near the base here, of course, this is the germanium substrate, then the wire starts, and the tin concentration comes up quite quickly, and we get to concentrations exceeding 10 atomic percent over most of the wire's length. This is in the shell region. And we can see evidence of this tin-rich material in the analysis of the X-ray diffraction data. Actually, we can decompose this peak for the nanowire diffraction into 3 different peaks of varying tin concentration depending on where we are, either down here, up here where it's more tin-rich, or in the middle. And they're actually quite consistent with the positions of those peaks in the diffraction scan. So the final slide I'll show on this, because the germanium tin shell is such a good emitting material, as we increase the tin concentration, it's possible to actually measure photoluminescence from individual nanowires. So this was an experiment that Andrew did. He mechanically removed nanowires from the growth substrate, placed them on a silicon substrate with template stripped gold on the surface to make a more reflective surface, and was able to observe photoluminescence from single nanowires. This is an example of one of these experiments. And by varying the excitation laser power, we can see that we start to observe emission at higher energies, as if we're beginning to populate the L valley of the conduction band by a spillover of carriers from the gamma valley in this pseudo-direct material. So I think this is very encouraging. We've shown a path toward achieving high tin concentrations in these shells. We can decouple the crystal growth of the shell from misfit strain by using the compliance of the nanowire core, and we can achieve some promising results along the direction of getting to direct gap materials. Obviously, there's more to do in the future in trying to implement these things in nano devices. So the summary here, understanding the role of tin chloride mass transport in our CVD process was very important for growth of defect-free shells and metastably high tin concentrations. The compliant nanowire substrate suppresses misfit dislocations and it increases the strain by increasing elastic tension in the core, preferentially lowering the direct gap in the germanium core. I didn't point that out, but we actually attribute these two peaks to the direct gap transition in both the shell, the tin-containing shell, and the highly tensily strained germanium core because of the coherency strain that exists in it when we grow these shells on it. The direct gap emission is consistent with the highly tensily strained core, as I just said, and we can measure room temperature PL from single nanowires. So I think this is a very promising direction for optoelectronics, or at least nanophotonics in the future. So with that, I'll thank you for your attention.
You can get to see me run, so.
Yeah.
For your first topic, so you have shown 70% bromine, 30% iodine halide. So I thought that you mentioned that this is complete solid solution over the whole range.
Yeah.
And then, do you have other ratios showing similar behavior of this separation?
It's a good question. So we've looked at a range of compositions from about 5% iodide to about 40% iodide, and we see this. We have not been able to grow films with more than 50% iodide, at least in the initial experiments we've done. Now, actually, KJ, your question is very interesting because it turns out that we observe in our diffraction experiments evidence that this is a metastable phase of this material before we ever shine light on it. It's growing into a high temperature phase of the perovskite that we can index very closely to a cubic phase. But we know that from the presence of twins and other defects that we see in this material, not the really obvious grain boundary type defects, but at a lower level, that it's likely a distorted cubic phase. So it starts out being a little bit unhappy anyway, because of that.
You can just nudge a little bit, then it goes to the other.
Yeah, and that could be important for why this happens. So it may be that there's a composition range that's most susceptible to this kind of phase separation.
Over here?
Yes, right at the back. Sorry, Dr. Dougal, come to you next.
Thank you for your beautiful talk. I have a question about the perovskite photoemission emission. So I just was wondering that how did you test your samples to get the PL emission? I mean, what condition you consider? Like you test your samples in air condition or oxygen condition or nitrogen? Because we already know that oxygen can passivate the perovskite surface and also fill in the traps. So this can have an effect on the PL emission and also either in the intensity or wavelength.
Right.
So I was wondering that what was your condition that you test your samples?
It's a good question. So most of our experiments have been done in air. We have done some experiments in a nitrogen-containing environment as well. They haven't been significantly different, but all the samples were exposed to air before they were illuminated. I will say, though, that the cesium-lead bromide iodide system is one of the less environmentally sensitive perovskites. So it seems to, but we do see if we keep samples and keep looking at them over a period of weeks, we do see shifts in the peaks. So it isn't. So it's important to be aware of that and comparing the data. Yeah.
So I want to follow up on KJ's question.
Sure.
If I think about this phase separation, so the entropy term is driving them to make a homogeneous
Yes.
solution. So now it will phase separate because the enthalpy term somehow change with light. And is there any theoretical model or experimental measurements on the enthalpy term when you mix the, I mean, they can make cesium lead iodine and cesium lead bromide. Has anybody done something like that?
Yeah, I think the one thing I'd point out is that it's not just light, it's also something that we observe in LEDs, so during carrier injection. So the way that I think the enthalpy term effectively is changing, but it's changing as a result of the occupancy of the conduction and valence band states. And if effectively as there's a perturbation, a local perturbation in composition that causes the electrons and holes to trap, then the free energy of the process is negative. And the more that they trap, the more negative it becomes, because you partition more and more of the carriers into that region. In terms of theoretical examination or studies of this, there have been a couple of papers that have come out since Hoch's original one, trying to analyze this. So I can refer you to those. I think that for me the question that I'd like to see resolved is what morphologically, how is this taking place? Can we visualize it as it's happening, as we're shining light or injecting carriers into the material? And so far it hasn't been easy. We can see evidence in diffraction, but we can't isolate that to particular regions of the sample.
Can you measure the diffusion rate of the ions?
Yeah, so there's been some really beautiful work done on that by Joachim Meyer at the Max Planck Institute in Germany. And what he observed is that this system, like a lot of metal halides, exhibits halide ion diffusivities that can be varied by orders of magnitude through doping, carrier doping. And in this case, the carrier doping can happen by absorption of light, or it can happen by carrier injection, or actually adding real dopants to it. So the diffusivity of the iodide in methyl ammonium lead iodide, for example, can go up by 4 orders of magnitude by shining light at room temperature.
My thinking was that since you know the recovery time of the material after you turn off the bias with light, then you could get a handle on the length scale of phase separation if you knew the diffusion constant.
Yes, that's right, possibly, yeah.
Okay, and one final question. I know there's lots of questions, but
Thank you for the nice talk.
Sure.
So my question is about dislocated microstructure for the quotient structure.
Mm-hmm.
So you mentioned that quotient structure, we don't see many dislocation. So I'm just wondering if it's possible to believe that the interface can play as a sink of dislocation.
Oh, well, I think that I don't think that there are dislocation. So it's an interesting question. Clearly there are dislocations in the substrate, but they're pretty low density. This is a high quality germanium substrate. Then we do homoepitaxy of the germanium nanowires on that substrate. There's no particular reason to expect we have greater concentrations of dislocations as a result of that. And then we grow the shell on top of the germanium nanowires. So if a dislocation were going to form, I would think it would happen in the shell and would propagate from the surface of the shell toward the interface during shell growth to relieve the misfit strain. We just don't see them. We don't see any evidence of dislocations in the wires. And all of the diffraction data that we've collected are consistent with coherency. The amount of strain that's stored in the core after we've grown a shell around it is consistent with a coherent interface. Yeah, we used to have a collaboration with somebody who did mechanical testing of nanowires in the TEM, and that kind of that was, I guess it's not active at the moment, but it would be an interesting thing to look at, yeah.
So I've gained the microphone back. Thank you so much for coming. Thank you, Professor McIntyre, for a wonderful talk.
Okay.
I've been thinking about perovskites in a whole new way, as well as tin germanium. This is a little gift and thanks from the engineering school for you coming today and being our distinguished lecturer. So
Okay.
thank you.
Thank you. Thanks, Amy. Thank you.